Mass, weight, and normal force. Mass is the measure of the inertia of an object, the resistance of an object to accelerate. In the SI system, mass is measured in kilograms. Mass is not weight. Mass is a property of an object. Mass is how much stuff is in something. It doesn't depend on where the object is located. On the other hand, weight is the force exerted on that object by gravity. If you go to the moon, whose gravitational acceleration is about 1/6 g, you will weigh 1/6 as much as you weigh on Earth. Your mass, however, will be the same. Weight is the force exerted on an object by gravity. Close to the surface of Earth, where the gravitational force is nearly constant, weight of an object of mass m is calculated as the force of gravity equals mg. Weight is shown as either capital W or F sub g or mg, since this is the equation for calculating weight. The acceleration of any object in freefall is g. Near the surface of the Earth, g is 9.8 meters per second squared in the downward direction. The Earth attracts all objects. Earlier in this unit, inertial mass and gravitational mass were defined. Alright, so here we have Newton's second law, and then any object on Earth is going to have a weight defined by mg, and that's the force of gravity upon that object. So let's say an unsupported object near the surface of Earth will fall down. If that's happening, if we are neglecting air resistance, then the only force acting on that object is the force of gravity. So if we plug the force of gravity into Newton's second law, we get mg on the left side equals ma on the right side. Another way to look at these two definitions of inertial and gravitational mass is that the mass on the left side of this equation is gravitational mass, and the m on the right side is inertial mass. Since they're both numerically the same, the equation reduces to g equals a. So the acceleration of any mass in a gravitational field is going to be equal to little g. An object at rest must have no net force acting on it because it's not accelerating anywhere. So if the object is sitting on a table, well, the force of gravity is still there. The Earth is pulling down on the object. It doesn't care that there's a table in the way. But additionally, what other force is there? The force exerted perpendicular to a surface is called the normal force, F sub n with a capital N. It is a pushing force and is always perpendicular to the surface that is pushing on the object. The table is pushing on the vase, exerting a normal force. The normal force is exactly as large as needed to balance the force from the object. If the required force gets too big, the table would break. The words normal and perpendicular are synonyms. This means that the normal force is always perpendicular to the surface, in this case the table. If neither the table or the vase is moving, then the sum of the forces acting on it in the y dimension are 0. So since there's no acceleration, the normal force must equal the weight of the object, mg. Find the weight of a 2,000 kilogram elephant. Alright, here are our givens, and then we're going to use the weight equation, where weight is the force of gravity, which is m times g. So m times g gives us 19,600 newtons. A car weighs 14,500 newtons. What's its mass? All right, here are our givens, and we're going to use the weight equation, where weight is the force of gravity, which is equal to mg. So first, we're going to solve this for m, mass. We're going to divide both sides by g, giving us this here. Take our givens, plug them in, and we get 1,480 kilograms. A book of mass 0.85 kilograms sits on a bookshelf. What is the magnitude and direction of the normal force that acts on the book? All right, let's draw a little free body diagram. So here's our shelf, here's our book, and the Earth is pulling down on the book with a force mg. Now the book is not accelerating up or down, which means this can't be the only force. There must be a force up that cancels it out. That is the normal force, the bookshelf pushing up on the book. And therefore, the normal force is going to be equal to the weight, mg. So we plug in m and g, and we get 8.3 newtons. And the normal force is upwards. The value of g can be determined by using a spring scale and a box of objects that have their mass printed on them. Weigh each object with the spring scale and create a table with the weight and the mass that is printed on the object. Rearrange F sub g equals mg to be F sub g equals gm. Just swap the order. Now this equation is in the y equals mx plus b format, where b is equal to 0. If we plot F sub g on the y-axis and mass on the x-axis, then the slope of the line is g. So here we have our data table. We weigh each mass with a spring scale and we record in newtons what the weight is, and then we just graph these. We put the force of gravity, so the force reading on the spring scale on the y-axis, we put mass on the x-axis, and now we have F sub g equals the slope of the line times m. So therefore the slope of this line on Earth, the slope of that line will be 9.8.